my pleasure to introduce Luca, who hopefully you all know already. So he's a postdoc here working on CMS, and he's going to tell us about Di-Higgs production at CMS.
Okay, thanks.
So no data. No data.
No data at all, no.
We don't mind, bro.
You don't mind? So, I actually have a couple of slides about real data. Come on, by CMS. So yeah, so I use this occasion since we are going by the speaker to talk to you about this paper that we recently submitted to PRD with TAMU, LHC, and some colleagues from University of Sussex. And it is about probing the electroweak phase transition at LHC. So at the beginning I wanted to do something a bit general about the Higgs searches at CERN, but then I decided actually to stick to our paper, so it will be a kind of really focused talk of what our reactor we are trying to do. So we are going to take a final state with more than 1 neutrinos, and we are going to test a new method to reconstruct invariant mass in system when we have more than 1 neutrino. And it actually worked quite well, so I will try to, to focus on this particular search. So I will start with some introduction, so you know what we're talking about. So we know that the standard model is the most fundamental field that we have in physics. It describes fundamental particles and their interaction. It looks very good, but it's not perfect. So there is a whole branch of physics that is dedicated to understand the neutrino nature that we know is not well described by the standard model. There is dark matter and dark energy that also are not included in the standard model, but we know that they are there. There is some more, let's say, smaller problem, like the hierarchy problem, and actually the last point is the one written in red, is the one that I will focus in this talk, that is baryogenesis. So the huge asymmetry that we have between matter and antimatter, and this is something that we cannot explain assuming the current, let's say, minimal version of the standard model. So generally, when we want to solve one of these shortcomings of the standard model, what we do is that we add some field, like a singlet or a doublet in the standard model Lagrangian. We get more particle, we extend the Higgs sector, and generally we could solve at least one or more of this problem. So there is not a perfect theory, but this is a very short summary of what usually the standard model can be extended. So we can start with one doublet that give us some mass to the vector boson, and then we have the one simple Higgs boson, that is the one that we observed. The simplest way to extend the standard model is simply to have a singlet. We can add it, and then we end up with basically 2 Higgs boson. And if the second one is actually more massive, more than like 200 and something GeV, it could actually decay in standard model Higgs boson. So we have this resonant Higgs production. And this is actually the model I will focus, because this is the minimal way we can actually solve the problem of the baryogenesis. And I will explain you how in a couple of slides. Just to summarize other extended Higgs sector, we could add a doublet to the Lagrangian, and then we basically end up with what we go to HDM model, and this gives us the 5 Higgs boson. We could even add a doublet and a singlet. This has the additional advantage that we solve what we call the new problem. So we totally solve the renormalization of the hierarchy problem in this case, and we end up with 7 Higgs boson. But as I said, I will focus in the minimal extension of the standard model.
So Luca, this gives you a matter candidate?
Yes, also, but we will only use it in the context of baryogenesis here. So this is the outline of the talk. I will connect the electroweak phase transition with baryogenesis, and then I will explain how this is linked to resonant Higgs production at CERN. Then I will give you a short introduction of CMS and LHC. You probably already know it very well, so I will go fast here. And then I will focus on our channel. This is what we are trying to focus on. You can imagine, as I will tell you in a few slides, that when we have the Higgs production, we have a lot of final state that we could consider. We pick one that is not one of the most favorite, bbyb, because it has 2 neutrinos. Well, we consider 2 lepton, 2 neutrino, and 2 big jets. So having 2 neutrinos is not possible to reconstruct the Higgs invariant mass, and we will prove that this channel could be as competitive as many others, like for BB gamma gamma, or BB tau. And this is the tools that we will use, something that we call the high mass estimator. So, and then, yeah, I will give you just an idea about a couple of searches that are ongoing at CMS exactly on this Di-Higgs production, even if they do it in the context of other benchmark model. So they are trying to solve something else. So this is the introduction. Let's talk about baryogenesis. We know that the dynamical generation of baryo-symmetry requires to satisfy what is called the Shakarov condition. So the first one is B violation, then we have CCP violation, and the factor of thermal equilibrium and breakdown of CCP invariance, but the latter is not really considered. So sphalerons here is in green because actually B violation is something that is allowed by standard model through sphalerons, so it's something that we can check. Concerning the CP violation, CKM metrics not enough to justify the current asymmetry between matter and antimatter, so something is written here on the side that is in red. And also, if we consider the minimal standard model, where we have only one Higgs boson with 125 GeV of mass, the electroweak phase transition occurs through a crossover phase transition in the universe, and this is something that I will show you in the next slide. So let's say that with the current model we are not able to satisfy the Shakarov condition, but a solution is possible. We could extend the Higgs sector. This means that we change the natural properties of the phase transition, and in principle the universe could have undergone a strong first order phase transition, even with standard model like this boson like the one that we observed. And the simple ways to do it is consider what I told you before, the XSM model, so standard model plus a so this is just a sketch of the Higgs potential, and as you can see, it depends from temperature. So if we only assume a single Higgs boson with large mass, this is the potential as a function of temperature. So basically we are in this situation with the Mexican half potential, and at early universe this was the potential shape. So going, let's say, when universe got cold, we smoothly went to where we are now, without any strong phase transition. In case that we add extra, let's say, boson, like a new Higgs boson, so we extend the Higgs sector, this is the, let's say, the shape that would take the Higgs potential. And exactly this is the, let's say, the scheme here is the strong transition, when we go from a region where electroweak or the symmetry was not broken to then where it's broken. And these give us to this bubble, let's say, of let's say this region where the symmetry is broken inside and outside is not, and then the interaction between sphaler and the bubble itself is what created this asymmetry between matter and antimatter. So this is, let's say, just the introduction about the model. And what we are considering here is that if we extend the standard model, adding a singlet, this is a kind of Feynman diagram that we could have. We have a heavy resonance here, heavy Higgs, that begin to standard model is boson. And as you can imagine, the final state that can be produced are a lot. So here in this plot, you can see the branching fraction of one Higgs versus the other, and on the z-axis you have the branching fraction value. So you could go from bbbb, that is the one that is the biggest branching fraction, to, let's say, some more disadvantaged channel. Of course, you want to pick up something that has a high branching ratio, but also that you can reconstruct. And the red star is in the bbyw, that, as you can see, has a high branching fraction, but there are two products. The first one is you have to material final state, at least in these final states. And also, you have TT bar, that, as you can imagine, will be a huge background for this channel, because TT bar will be exactly bbyw. So this is something that we call irreducible, and also the difference in cross-section is huge. So this is what we want to show you, that can be actually competitive as other channels. This is the team, so you know LHC, you know Tau, you know me. And these are our friends from UMass University, Sussex and Durham, and they are, let's say, the theorists that are beyond our paper. We actually only took care of the experimental part. So let's give you an introduction about LHC and CMS. You probably know it, so we go very fast here. This is the LHC. We have CMS in front of Atlas. Atlas is close to the seat of Merene, where most of the offices are. This is the building 40, maybe one of the most famous. And that's Geneva, and then we go straight to the lake. This is the fountain. So when we talk about the Higgs production, we probably are referring to high luminosity period or anyway to we need high statistics to draw these kind of processes because they are not common. So I will give you a short introduction of run 2 because the first analysis on the Higgs are actually starting now and they are quite interesting. So when we say run 2, it means that we're taking data 13 TB and also we already collected 14% by 2016. This is twice what we had before with 8 TB data, so it's a huge instantaneous luminosity that we have now. The big advantage of run 2 is that if you look at the luminosity ratio, this is the part of luminosity 13 TB versus 8, are really favorable if you want to produce heavy resonances. So as a function of the resonance that you want to produce, you can gain from a factor 2 to actually 100 if you look at the resonances. And this is something that of course is going in favor of this kind of searches. As I say, luminosity is ramping up, and this is no way to increase luminosity, we're also increasing pile-up. Pile-up is the multiple interaction that we have over batch crossing. This year was 24 in average, but it's expected to be much more at high luminosity. So when I say high luminosity, I refer to the period of data taking of LHC that go from 2022 to 2035. So we really want to exploit at the best the LHC performance. And we are planning to accumulate 300 inverse femtobarrel data by the end of 2022, so when it will finish 22. And then during the whole high luminosity, we will reach up to 3,000 inverse femtobarrel. So this is a huge amount of statistics. And finally, coupling, the self-coupling of the Higgs or the Higgs production here can be probably much more than with simply the few femtobarrel that we have at the beginning. This is how an event display would look like with 100 vertices. So now we are at 24, where for high luminosity is planned to reach at least 140. That is huge. This is a small picture, but you can see that how the travel looks like. And this is actually a bit optimistic in the meaning that it will be more, and also the real problem are not traps, but are neutral deposits. If you're a neutral hadron, then you cannot link them to any vertex, they go to the detector and they overlap to your signal. This will be a huge pain that we have to work with. So a lot of effort in the CMS are currently ongoing to be ready, because we cannot switch the luminosity to high luminosity tomorrow because we are not ready, but we have time to develop the strongest reconstruction algorithm to mitigate this.
So the timeline is 2025, right? I cannot read it from here.
Yeah, so 22, we should start the long shutdown 3 that it will last until 2025.
Okay.
So this is the period that we need to prepare, and then it will start, of course.
That's the rest of the paper.
Mm-hmm.
Is that the most recent schedule? Is these
No, this is not the most.
year over year?
Yeah, actually I took this from my PhD thesis, so I'm not really sure it's updated. Okay. 1 year ago it was like that. I should recheck. So this is a sketch of the CMS detector. Here you probably already know everything. You can just say that it's an onion-like detector. It has different layers, and each of sub-detector is measure a different interaction of particle with matter. So basically we can reconstruct every particle in the standard model, except for neutrinos. But if we, let's say, measure the transport momentum of all the particles producing the collision in the transverse plane, we can give any imbalance to neutrino that are escaping the detection. So this is our indirect way to quantify the presence of neutrino in a given interaction. As I say, for this paper that we submitted, this is not a CMS paper, this is a Philo paper. So we didn't use any CMS tools. We used Delphis. This is a free software that basically simulates the CMS detector just using parameterization. So there is no giant, there is no real physics in the reconstruction. There are just some performance like efficiency, resolution, stack, and this is what we use to reproduce CMS results. So everything has been done outside from CMS. So this is the analysis. So now that we go to the experimental part. This is the channel that we want to look for. You can see we have 2 million, 2 jets. So I'm really looking at the diagram. If we want to find for this kind of signature, what we need to do is to look for 2 jets that are originating from quartons. We need some missing between because we have 2 neutrino. Also, we know that the jets are coming from an Higgs boson, so we could impose the Higgs mass here to add a further constraint. And then what we want to do is to look at the kinematic, so basically the angles between electron and jets, and see if in this way we can see something that is peculiar of this decay. The main backgrounds are TB bar, large cross-section, and be exactly the same from state, so we really have to be smart with TB bar. And then there is Variate, TW, and resonant processes, but we can neglect almost all of them. Maybe Variate will contribute a bit, because it has a very large cross-section, but there is no missing T and not living order, there are no jets. So Di-Higgs plus the MBA we will apply will mostly kill all of Variate. So just for the purpose of these feasibility studies, we will only focus on signal and TB bar. These are the only two characters of this analysis. This is how we generate sample. Basically, with signal, we generate sample using L++. And in one slide, I will actually focus a bit on the phase space of XSM model that we're using. And so for now, just let's assume we generate some sample with L++. For TB bar, we use POEG next to living order. And then we do showing and analyzation with HEPEC. And then with LFS, we allow Electroweak quantities. We have a very, let's say, simple selection at the very beginning, so we require Leo to be inside the CMS acceptance of the jets, and then we have some basic class on the transverse momentum. Also, when we use DELFS, we can say what pileup scenario are, and we are using now 40 pileup. That is not realistic in terms of high-luminosity, but if we assume that for high-luminosity we will improve our understanding of the detector and how to mitigate pileup, this is something that is maybe realistic with the current reconstruction technique. So I would say that we generate the signal, and this is how we choose which signal points to generate. So what we did was a scan in the Higgs that here is called M2 mass, and cos theta. Theta is the mixing angle between the doublet and the real sim that we added to the Lagrangian. So in this phase space, we can simply generate random point and then test if they actually allow this dynamical generation of barrier asymmetry. So each point that actually satisfies the problem of the baryogenesis, solve the problem of the baryogenesis is kept, and is shown here in the map. And then we basically select two subset of points. The first one is what we call optimistic scenario, that represent all the points that maximize the cross-section temperature ratio R LHC. And in violet, in purple here, we have the one that minimizes it. So among all the possible phase space, we select some sample divided in mass, so that we are scanning with the whole Higgs mass up to 1 TeV. We came up with these two different benchmark let's say points, and you can see they are quite, they are not continuous distribution. You would expect probably a continuous distribution, but it's not, because from point to point, several parameters of the phase space are changing, so it's something that is a bit segmented.
Look, avoid this curve Mars 800.
Sorry?
Avoid this curve Mars around 800.
About here. This I don't know if there is a specific reason that this happened. So this is what has been found. I don't know if there is some important physical reason why this should happen.
So what are these two? Could you please just repeat or something? So
Sorry.
what are these two? Optimistic and pessimistic?
Optimistic and pessimistic.
So how do you define your optimism and pessimism?
So basically they are defined in terms of cross-section temperature ratio at LHC. Optimistic because these are the points that will have highest cross-section at LHC. And these are the ones that will be less favorable to be found.
So you can see the green point and the
Yeah, so basically among, in all our phase space where we are generating signal sample, we pick up, I don't know, like the 12 that give us the best cross-section temperature ratio, and the 12 that give us the worst. So at the end we have this kind of interval where if new physics appear should be.
Yeah, for large mass now I understand, because when you go to large mass, at that time mass is the only culprit. like
Oh, I see.
everything is going down as a function of mass because everything.
Ah, right.
So
Okay.
that's why.
It makes sense. Yeah,
Luca,
you're right. Good question.
So what are these vertical lines and left plots? Does
Uh,
that mean like your
so-
range is all to the right?
No, so this is taken from an old paper that telling you what kind of phase space we can probe a different collider. So here they are testing like a circular collider, plus minus minus. So in terms of LHC, you can forget about it. But you can see also here, this is the sensitivity that you would get looking for optimistic scenario. And this is the example of 100 dB collider with some different luminosity at 14 dB. So this was done in a previous study where they see the best collider to look at this mass point.
Right, so for this study, vertical lines do not really
No,
matter.
no, so simply take
So it's
the-
just the dotted lines that are.
just the dot. Each dot is a different phase space.
How do you select the ones that correspond to LHC?
So basically what they do, they compute the exponential and they see if the shape is compatible for what can create baryogenesis. So for each point there is then a study that the theory from UMass, the guy from UMass did, that say which one would actually allow baryogenesis or not. And this you see through the exponential. So basically these are the sensitivity that you get, but this has been obtained with a really rough estimation. They just assume some acceptance of signal and they just draw a line. So what we are trying to do is end up with something like that, but specific for our channel with a much more well-defined strategy. So this is just few number. These are the 12 points that correspond to optimistic cross-section. We have 12 points. What I actually care, since I'm experimentalist, is the mass of the point and then the cross-section time differentiation. So we basically select the points that, ranging from 300, 250 to 850 GeV in mass, and this is the cross-section that go, of course, decreasing. So if you see the previous plot, this is log scale. So around here, the situation became quite desperate. But also, I want to remember that this analysis we are doing at the end will be model independent. So all our paper is focused on baryogenesis, but once we study the bbyy channel, we can actually overimpose any signal that we can test any hypothesis that we want. So having a good analysis, the channel is valuable even if it's not able to test this specific model, because there are many others can be tested.
Just you are looking for a resonance and Di-Higgs production.
Yes, exactly. So this is just to give you an idea of how to spread the situation at the beginning. All these numbers are referring to 300 inverse femtobar of data, and we consider TD par times the branch ratio to mu. So all the analysis is done with mu, but it's basically the same with the electron. We did it simply for convenience. Then we can assume that the electron channel will be sensitive as the muon one. And as you can see, we have 3 million events from TD par. Then in P1 we have 600 at the end of 300 inverse femtobar, and this is the most optimistic scenario, because then at B12 we have like 0.5 events. So you can see that the situation is quite hard. Anyway, this is what we have, and we want to try to do our best to be sensitive to eventual signal. So this is the basic selection. What I was saying before
So
is
just before you
Yeah.
charge it, probably check it. Do you know the TT bar production cross section from this resonance? Like you'll have like a HTT at loop and then just a pair of TT bar appearing from this resonance.
we can check that.
Why I'm saying, because since you are looking at the background, and that would come to your background as well.
Yeah.
And so at the end, since your background is similar to signal, so that I'm thinking that probably that TT bar branching ratio would be similar. So it would be kind of you are hitting the background at the same time. So
Yeah, but
Or you can see the resonance.
exactly. So that's also
No, this would have a different kinematic problem, right?
Yeah.
Because we have a whole selection that it's like,
no. When you choose TT bar at that time, you just.
I mean, we have the same number here at the very initial stage, but then we have the whole selection also based on kinematic variables that we feed the depth to the MBA. So probably then you would.
Suppose I give you another source of TT bar. It doesn't matter whether it's coming from resonance or anything. Just a top and T-top being present in the final set there. Your cuts are just like that. So what I'm saying, through this resonance mode, there could be a source of TT bar.
Okay. But you mean that this 3 million would be 3 million and 600? No.
I don't know.
Okay. I see.
Whether it's
Okay, yeah. Yeah, this is something we will include when we make the analysis.
But you don't expect a small branch fraction H to TT bar.
no, just through this loop.
Yeah, that's what I mean.
Yeah, so
Could be the right branch.
Yes.
Okay. Yeah, maybe I can come back to this later. Anyway, so this is our basic selection. So we require for muon jet, missing transverse energy, and then we ask for 2-beta jet. This is done using what we call combined secondary vertex. Basically, this is an MBA that take the impact parameter. Basically, we look at all tracks inside the jet. We propagate it back to the vertex, and we take the minimum distance from the vertex. This is also an uncertainty that is the significance of the impact parameter. So, number of tracks, impact parameter, etc., is also fed into this MDA that give us a discriminator that we call CSV. And we use a medium working point that is 70% efficient and has a mistake of 1.5. Also, the second big jets at the beginning was also medium working point, but then we decided to relax it. So we asked for, let's say, for the 2 jets with the highest CDS value. But the minimum is 1 million and 1 loss. And after this selection, you can imagine this is not damage a lot T bar because final state is the same. So we are in this kind of situation after the preselection. So let's look at some kinematic distribution that we will use it. So first of all, we look at the jet invariant mass and the electron. So you can see that already from this distribution we have some kind of to differentiate the two. Also, the interesting thing is that the invariant mass is not dependent on the High-Luminosity mass. So going from low mass, that is B3, to high mass, that is B9, all this distribution is very similar to what the varies probably.
So the left one is dielectron and the right.
Yes, the right is the jets. It's not picking exactly a 125 GeV, and the reason is that the jets have a component of the decay method that go into neutrino that we can reconstruct. So we are missing part of the B energy. This is actually recovered later. So this is RICO as we can reconstruct. But you can, in principle, impose the X mass and take back the neutrino component that you lose to bring it back. And this is actually what we do later. And this also corrects the missing energy. Because also the neutrino from the missing energy in the big jets affect the missing energy measurement. So you will see later. So this is delta R, basically between the 2 lepton and the 2 jets. We actually use even more different kinematic variables of delta R between the 1 lepton and 1 jets, but here there is just 2 of them just to show you. So already from this plot you can see that the discrimination between the ground and signal changed depending on the signal mass. So what we decided to do was to develop a multivariate analysis that is different for each mass point. So basically we trained 12 MDA, one of each given mass, and this is what we will use later, because
so
most of the variables...
B3, B6, B9, so it's going in...
This is high mass.
B9 is the highest.
Yes. The highest is actually B12, so I took...
Oh, you did, but for that, for those three, among those three, B9 is the highest, and B6, and B3 is the lowest.
Exactly. B3 is actually a bit peculiar because B3, the High-Luminosity here, has exactly twice the top mass. So it's actually worse point because then when you look at the kinematic, you see that they have the exact same mass, and you will see next slide why this is important. So exactly, this is what we're talking about. So this is the transverse mass. Transverse mass is defined by this formula. It's quite standard component, variable. And you can see that it does not offer a very good discrimination because our TT bar and basically the signal is mostly peaking around the same region. What we use is another variable called MT2 that offer a much better discrimination. So MT2 treat the lepton and the jets as a single object. Since we have 2 jets and 2 lepton, we have 2 different versions of MET2 depending on how we couple a lepton and a jets. We do both and we take the minimum value. In these ways, you can imagine like an estimation of transverse mass in system with more than 1 neutrino. And you can see that the discrimination here is much more powerful because this is TT bar. Unfortunately, B3, since it has the same mass of twice top mass, it's actually peaking exactly in the same region. But also B3 has a much higher cross-section, so there is this interplay between that high mass that is more different from TT bar, but actually has smaller cross-section. And this is the preselection we do. So this is the first one that I just described. Then we have a very loose preselection, depending on the variable I showed you a few slides ago. But we keep it very loose. In fact, we only lose 3% of signal for each mass point. Here, each bin is a different signal. So from B1 to B12, we are basically 3% efficient, and we reject about 40% of TT bar. So this is just to clean a bit the sample, and then our multivariate analysis will do all the heavy jobs of differentiating the two. So this is still the situation after all the studies. So the principle of the MBA is go from this situation to a bit easier situation, here with a mirror, if you see it. So basically after the preselection, we try our MBA for each different mass, and then we use it as a discriminator, and then we have the final distribution. And here is where we will use our heavy mass estimator. So basically here we will reconstruct the invariant mass of the Di-Higgs using our new approach. So I will go through the MBA.
So did you use that like a delta phi between B and lepton?
Yeah, there is also delta phi.
It
Yes.
does not help you in terms
A
of
bit, yeah.
yeah. Not a lot.
Not a lot. What mostly is helping is imposing.
So which one
mass.
is
Hmm?
which one is the most helpful, like for that?
So MT2 for high mass?
No, for the TD bar point, TD bar and that heavy is B3 point.
B3.
So what's the most helpful?
So I would say that both this distribution helps because they don't change with the mass. One is the X mass. So we constrain that the 2 bit jets are coming from an X, so this helps.
That Higgs window cut.
Yeah, the X window cut, PT, and not much more actually.
Okay. So everything else is kind
It's helping, but
Not
not
that.
striking. Yeah, not that much. So these are how, we feed. So the MBA is basically fed with all this distribution, and you can see this is B7. That is actually a, let's say, quite high mass and TT bar. Signal is in blue, background is in red, and you can see that by default there is no real cut that one could put by eyes. I mean, you really need an MBA because there is no way here to come up with a new selection. These are the invariant mass and something related to the XPT that actually help, and MT2. But except all the other not helping much. These are also the correlation metrics between the variables. So you can see that each variable is 100% correlated to itself as expected, and then the matrix is symmetric. What is actually interesting is that all these delta R, PT, and the transverse mass are actually quite independent. They are, let's say, centered around 0. So we don't have a very strong dependence about variables, and this means that they all can help. They don't share the same information, except maybe the invariant mass of BB and delta R of BB, but we decide to keep it anyway. This is for background, this is for signal. Once we do this, we feed it to the MBA. This is an example of BDT, and what you can see are the 2 discriminators. So in principle, we could cut in this discriminator and reject everything on the left. And for instance, we could cut here and keep all this signal and just remain with the small tail of TT bar. If you want to see in terms of background rejection and signal efficiencies, this is the plot that we usually show, and we want to be on top right. We want to be here. We try BDT and basically narrow network, boosted decision tree, likelihood, and KNN. All these algorithms give you very similar performance, so we decide to skip to BDT because it's well known and broadly used. So this is how we choose our selection. For each possible cut, we compute the sensitivity that is signal over square root of signal past the ground, and at the end we come up with a cut that is located on the minimum. In our case, for this sample here. So we only keep this part of TT bar, all the rest is rejected, and then we keep the signal. The bad news is that this distribution normalized both to 1, but in real life, this is much bigger than this one. So even after this selection that gives you 50% efficiency or signal, we are keeping 50%. And we also are basically rejecting, well, we are keeping 0.0038% of the TT bar. Even in this case, when we normalize to the real cross-section, we have 91 events of the ground and 10 events of signal. So still the situation is bad, but not so bad as before. So that's the best we was able to do. If we compare low mass with high mass, this is exactly what we're talking about. The MBA is much more efficient at high mass because the kinematic is much more different. But here the cross-section is much higher. So there is this kind of interplay. And this is where we go to our final weapon, if you want, the high mass estimator. So now we have the MBA, we are able to have some decent signal at the ground number. We want that the signal now is resonant. And since it has 2 neutrinos, it's not. So this is the situation. We can impose 4 equations. We can say that the x momentum of the 2 neutrino is equal to the missing energy on the x-axis, same on y. We can assume that the 2 Higgs boson are on shell and only W boson is off shell. It means that one of lepton neutrino system will give you the invariant mass of the W boson, and the other one will be between 20 and 45 GeV because it's off shell. And we can impose that the dilepton and dineutrino system altogether will give you the Higgs mass. So at the very end, we have 6 unknown that are the neutrino momentum on the X, Y, and Z. And we have 4 equations. It means that we have 2 unknown. If we could know somehow 2 of the variables that we don't know, we could solve the system and find a heavy Higgs mass. So this is not what we are doing, but let's assume we randomly generate eta and phi of 1 neutrino. We could feed them into the system of equations and find a solution. We don't want to randomly generate eta and phi of 1 neutrino, so we can estimate from simulation the distribution of eta and phi. We can create a PDF, and then we can randomly generate several times eta and phi of 1 neutrino, and every time solve the system. We call the process of, let's say, 1 generation, 1 iteration. It means that for each event, we generate 1 million of neutrino phi and eta point according to the PDF. So we follow what we expect from simulation. And for each event, we have 1 million of possible masses. If we plot these possible masses in an histogram, it looks like this likelihood here. And then we can try to estimate the correct heavy Higgs mass by looking at the most probable mass. That is the one that appears most of the time. And this has been compared with the true mass of the heavy Higgs. So in this plot, this is only a single event. So each event, it means 1 million of generation. We come up with this likelihood. And then here is the mass that we estimate using only Rico quantity. And it's very close to the true mass. Now the situation is not so easy. I mean, what I described to you is a simplified version of the actual method. What we actually are doing is that taking this variable and also smearing the missing ET according to the missing ET resolution that we have in our detector. We also account for miscorrection from the jet. So we corrected the jet to recover the energy lost in the neutrino and the jets. We correct the PT, and then we recorrect the missing ET again to include what we lost from there. We smear these 2 quantities. Also, W mass is not a single number, it's a distribution. And at the very end, these are the final invariant mass that we are able to reconstruct using only Rico quantity. So we start from 2 neutrino, we end up with B9, B6, and B3 that are actually peaking to the correct value. There is some resolution, but it's actually quite good. So at the very end, we are able to have a distribution for TT bar. So for TT bar, we do the same, but we are imposing equation that make no sense because there is no X there. And good things is that most of the time there is no solution. We try to solve it. There is no solution because we are imposing random equation. So we neglect the event. And this only happens for TP bar. So if you want, this is a further selection. If admit solution, we pass to the next step of the analysis. So TP bar is basically at this long tail that is falling down, and then B3 is resonant, B6 and B9 are resonant. And this is, let's say, the way that we think we could improve this particular application channel, together with the MBA, of course. So this is the distribution before the MBA. Before any MBA, just at preselection level, we have a huge amount of TP bar, and then we have the heavy, this is what I would call HME, that should be the mass. It's actually really difficult to pronounce, so let's say mass. So this is the Higgs mass that we reconstruct, and you can see that it's resonant to the correct value, and then the analysis is much simpler because you just want to find a peak in a falling down distribution. That is most of the analysis where you have some resonant production. Bad news is that MBA also, let's say, will select some TT bar only in this region. So let's explain this again. In this plot, you can see the mass of the Higgs as a function of the HME probability. The probability is the value on the y-axis here. So more is peaking, more is, let's say this number is high. This is not something that we use in analysis, just to show this plot in 2 dimensions. So what you can see is that for B7, so for signal, all the mass is located around 550 GeV as expected. And when we apply the MBA, only events around the peak survive. The MBA have no knowledge about the mass. The MBA only have BT and delta R. But in somehow, of course, it's able to neglect everything that is around and just keep things in the peak. And this is fine because we go from 28 events that we expect to 10 events at the very end. So we are highly efficient, so we keep everything on the peak. For TT bar, this is what's happened. We have something that is peaking at very low mass in heavy, HME mass. And when we apply the MBA, we only select event in the same mass region, because the MBA is able to figure out somehow the good kinematic, and the good kinematic that's mimic the signal is the one that is peaking in the same point. So bad news of the methodology is that at the end we have 2 distributions peaking in the same region. But still, we are able to, let's say, disentangle more the 2 distributions. And also note that here, after preselection and basic selection, we have 430,000 events, and we add with 130. So it's a huge discrimination that we have from the MBA. So what is fundamental, just to derive limits and know how good is this analysis, it depends on how well we know TT bar, the systematics on TT bar. Because even if we have, I don't know, 100 events, but we know it very well, then it's done. But if we have a large uncertainty on this 130, then the limits will go much worse. We do not have data, but we plan to use data-driven technique to find this TT bar, and this is the way that we explain the paper we will do it. The idea is to create a control region. It means that you define, for instance, taking events with high jet mass or dilepton mass, we can select a region that is mostly dominated by TT bar. Then we further apply again our MBA, train it in this region, using the same efficiency we have in the signal. And then we can do the same for data and simulation, TT bar. And we can compare the 2. Since this is mostly dominated by TT bar, we can compare data and simulation in this region, and we can basically find a scale factor to reweight the TT bar depending on what we see in data. So this is the control region, how it would look like. This is signal region, this is control region. We do basically this for data and for simulation, then we can compare, and we can reweight the TT bar as a function of the mass and apply this scale factor. And here, the systematic will be mostly driven by the statistic that we have in this control region. So after some studies, we decided to be a bit conservative, and for TT bar, we are just assuming, as I say, this is a bit hypothetical. We did not do that since we have no data. This is simply a feasibility studies. But being a bit conservative, we decided to be the 3% uncertainty of TT bar in the low mass region, 5% in before, and then 12 and 15% in the high mass. Yeah, it's important also to say that this analysis strongly depends on how well we know TT bar, and we assume that at high luminosity or in the future we will improve our understanding of TT bar. So probably, say uncertainty will go down. For signal, this is, yeah, as I said, this is just a rough estimation. We decided to use 10% because this is what is used in most of analysis by CMS. This is simply an example of all systematic that usually are included in one analysis. So this is integrated luminosity, scale factor for trigger and ID. Then we have theoretical uncertainty on PDF and repeated awakening. In general, we have something about 7-8%. We decided to use 10% because to be conservative. And these are the final limits. So you can see in dashed line the expected so the cross-section that we have in our optimistic scenario, and then we have the observed limits. This is with 300, this is with 3000. So of course a high luminosity give you an exclusion up to 700 GeV. So in this way we could exclude the model up to here. Also you have, yeah, I have to say that here we are including also electron in final state, muon, and also we are combining, we are assuming an eventual combination of CMS and Atlas. So there is a factor 2, let's say, statistic coming from an eventual combination.
So you said that you include the electron too?
Yes.
Here.
Yeah, here. Yeah, we are assuming that the channel with electron gives us the same sensitivity that for muons. What we did not include is an eventual combination with other final state, because we would look for other decay in, I don't know.
So how about pileups? Did you include pileups?
Pileup is 40. That is something, because now
For
there are,
3000 10 to 1 meters. For 3000 in
what we
10
will
to
have
1
here,
projection.
yeah, so 40 is less than what is expected, but it's also true that our reconstruction technique is the one that we're using now. We are not using the feature of detector.
So we do.
Yes, when we actually have a granularity, also there is a timing device that has been studied to actually tag by time particle and then select the one only around the correct vertex. At the end, this would drop the effective pileup by a factor, I don't know, more than 10 probably. So at the end, it's something realistic, let's say.
So post-prop include the mu.
Yes.
Mu. Post-prop.
Mu? AE? Yeah, E, yes.
And the combination, I mean,
In mu, yeah, also mu, and CMS analysis. So yeah. This is just to show you the power of using a shape. So after the MBA, we could derive a cut-and-count analysis. So just look at the bar number and signal number and derive the same analysis, and these are the limits that we get. They are quite bumpy because if you remember, the systematics increase with the mass. So every time we increase the systematic, we have a jump, of course, in the limits. This is washed out when we use a shape, because in a shape we are less sensitive to an increase in systematics. So you can see that the effect of using reconstructing the mass is actually helping a lot. This is also a comparison with other channels. So this is the sensitivity. We draw a line to 5 that usually are the sigma to claim a discovery. And what we are seeing is that in general we should be able to make an eventual discovery if new physics exists up to 700 GeV using the wall 3000 inverse effective Pernie. But the most interesting plot I think is the one on the right. Here we are comparing the sensitivity. So here there is no signal. This is simply the observed limit model independent. And here we are taking BB gamma gamma, BB tau tau, and BB WW. And you can see that all of them are quite compatible. So what we wanted to prove is that this channel will be quite useful if you want to combine it with the other, because actually sensitivity is quite good. Of course, this is just a rough estimation. All the limits has been normalized with the same luminosity and branching fraction. So it's a fair comparison, but it's not 100% fair because, of course, our estimation of systematics has done really roughly, so things could change. But our point is that this channel should not be neglected, especially in the final state with 2 and 3. This is some results from CMS, so everyone is happy, you can see data, and actually you will see data here, not here. So this is the bbbb resonant and non-resonant, actually is also non-resonant researchers. These are the public results from CMS. This channel will be really, really good at high mass because they will use a clustering technique that uses AKA jet. AKA basically is this particle flow where the cone is 0.8. It means that at high mass, the two B jets will cluster in one single jet that will be peaking at the X mass. So then what they are looking is simply two jets, very broad, each of them include 2B, and both are peaking to 125. And this actually is not limited by high mass, it's actually even probing at high mass. So this is the channel to look for high mass discovery. They actually divided the analysis into regions. There is one at low mass where still they can resolve each B jet, and then one at high mass where they cannot resolve and they use this AKA8 clustering algorithm. They also look at the invariant mass versus, well, of the two-day jets. This is simulation, and you can see how the signal is basically peaking at 125, 125. And also they have the advantage that they are here. They are in top of these plots. This is the channel with highest branch refraction. So they have all the, let's say, the good advantages to have good performance. This is also the output of the boosted decision tree when they look for standard model Di-Higgs and also QCD and TD bar. So this is how they could perform, let's say. This is BB gamma gamma, also is very useful. Branching fraction is a bit lower, but gamma gamma also gives you a good handle to go straight the X mass from the two photons. They are not looking for our signal, they look for spin 0 and spin 2 resonances, assuming this random sample model. And these are the limits. Also them are basically dividing the analysis into region. In this region, the two big jets are so boosted that they are basically merging into a single jet, so they use a different algorithm of clustering. And in this region, they actually can resolve the two big jets. And this is something that probably we also should do in our analysis. We could, clusterize jets in a different way at high mass. And this is the distribution, how it looks like in their case. This is the total invariant mass. And okay, so that's it. So I hope you enjoyed what we did. It was interesting. We basically proved that bbbw could be an interesting channel for probing electroweak phase transition of CMS. We find out that with 2000 per atom we were able to do an eventual exclusion until 700 TP, but also we could reach the 5 sigma for a discovery. And still there is much room for improvement. One of the main things that I would like to mention to you is that so far about this likelihood, we are only taking the most probable mass. So we basically look for the minimum and take the mass that correspond to it. What we could do is to take the whole shape, because also the sigma of the distribution, the shape itself, could give some hint if this is TP bar or not. So what we would like to do in the future is just to feed it to the MBA, the whole shape, and see if FBA can do something better than just taking the mass. Yes, and that's it.
So I have two questions.
Yep.
Going back to this the probability distribution.
Which one?
The probability for this. Yeah.
Yes?
Yeah. So I'm guessing it's a kind of typical. And if that's the case, do you understand the structure and form?
I think this is simply a fake minima. You know, when you minimize something, you don't always have.
Stories like this.
Yeah, sometimes you have some fake minima, and I don't know. I don't think there is any special reason for it. I simply think that sometimes you have this kind of shape. So if you scan the whole area, then you find the real minimum. But I think it is expected that it is not simple Gaussian.
But then how consistent is the shape across the net? If you want to use the shape in your MBA later.
This is something that we have to test, in fact. I think that this could be promising. We didn't do any detailed study. What we should do is maybe at the first simply print out 1,000 of this plot and see how it looks like for TP bar and signal.
Sure.
Because I would assume that TP bar will look much different. We tried very quickly, we see no gain, but I think we should dedicate more time to study the shape. didn't do it because we were in a hurry to submit.
And the second question is what the Pascal asked. So this H to get to TT bar.
Okay, you mean High-Luminosity?
Yeah.
Okay.
In this case, I don't know branching ratio, but he said it could be large. Then you essentially since the TT bar resonance from the whole.
Yeah, but then there is no standard model X, right? There is only High-Luminosity.
No, he has a
No. We can have standard model with
So it's
the one loop diagram.
okay. I don't know.
Do you have a guess how big it would be?
No, I don't know the parameter space for your model about this. Generically it can happen. I don't know what's the story, what's the branching ratios and all this stuff. No. That's why I'm asking you to really consider.
And if that's the case, there's a TT bar resonance search. So it's good some parameter space can be removed. So that's the question for me.
Yeah, I will ask you guys.
Yeah.
I'll compare it with something.
Otherwise, good. Thank you.
Any other questions?